Welcome to this deep dive into cutting-edge AI research. Today, we're really dissecting a fascinating paper. It offers a surprisingly simple take on fine-tuning large language models for reasoning.
Yeah, specifically for mathematical problem solving, which is obviously a hot area.
Absolutely. And for those just joining, here's the quick version. This paper argues that a really minimalist method called RAFT, it just trains on correct answers, actually holds its own against complex reinforcement learning like GRPO or PPO.
Right. It turns out a lot of GRPO's benefit seems to come from simply filtering out prompts where the model got everything wrong, not so much the fancy reward math.
Exactly. And they even propose a new simple method, Reinforce-Rej, which filters out both all wrong and all correct prompts, and works pretty well.
So the big takeaway, maybe, just maybe, smart sample selection is more critical than super complex algorithms for this kind of task.
Okay, so let's properly dive in. As you shared this paper with us, a minimalist approach to LLM reasoning, it really jumped out, didn't it? Going back to basics when everything's moving so fast.
It really did. And I liked their focus on verifiable reward settings. Like math. It makes the comparisons between methods much cleaner, much more rigorous.
Yeah, that makes sense. Especially with models like OpenAI's O1, DeepSeek R1 making waves in reasoning. We hear a lot about reinforcement learning.
We do. PPO, proximal policy optimization, is kind of the default, isn't it?
Right, but it's complex. You've got the critic network, all the computational overhead. This paper kind of asks, is that always needed?
Especially, they suggest, because LLM generation might be, well, a bit more deterministic, lower variance maybe, than typical RL settings.
Interesting point. So that opens the door for simpler approaches.
That's the idea. And they look at a whole bunch of Remax, RLOO, different flavors of Reinforce, even the newer preference optimization stuff like SlickHF and DPO. Sets the scene nicely.
Okay, so let's get into the nitty-gritty then.
Yeah.
Starting with RFT rejection sampling fine-tuning. You said it was basic.
Almost laughably simple, conceptually. 3 steps. 1, get a bunch of prompts, generate, say, answers for each. 2, check the answers. Keep only the best ones, usually. The correct ones for math. Throw away all the mistakes.
All of them, just gone.
Yep. Step 3, fine-tune the model only on those good, correct examples.
Wow. So it's like, just show the model success, forget the failures during tuning. That feels counterintuitive, maybe? Doesn't negative feedback usually help?
That's the standard thinking, absolutely. And the paper does mention STAR, the self-taught reasoner, which sounds a bit similar.
How is RFT different from STAR then?
Key differences. STAR often restarts training from the original model each time. RAFT keeps fine-tuning. STAR might use greedy decoding, just one answer, while RAFT samples multiple to find a good one.
Rejection sampling versus greedy.
Right. And STAR sometimes gets the answer in the prompt to help it generate reasoning. RAFT doesn't. So RAFT is, leaner.
Got it. Okay, moving on. Vanilla reinforce. That's more standard RL, isn't it?
Foundational policy gradient, yeah. The core idea is simple. Tweak the policy, the LLM, to make high-reward actions more likely, low-reward actions less likely.
So if it gets a math problem right, nudge it to do similar things again.
Basically, yes. You collect trajectories, the model's responses, and update the policy. For LLMs, they often do this at the token level.
And the paper mentioned importance, sampling, and clipping.
Right, because you might do multiple updates on the same batch of data, the policy changes, importance sampling corrects for that drift.
Okay.
And clipping, borrowed from PPO, just stops the updates from getting too crazy large. Keeps things stable.
Makes sense. Now, GRPO. This one's been getting attention, especially with DeepSeek R1 using it for math. You said the details were a bit murky.
Yeah, not super well documented publicly, but this paper reverse engineers it, essentially. They frame it like reinforce, but instead of raw reward, it uses an advantage function.
Advantage? How does that work here?
Okay, so for each prompt, you get responses again. Then, for each token in each response, you calculate its advantage. It's roughly the reward for this response minus the average reward across all on-responses for that prompt.
So how much better or worse was this specific try compared to the average try for that problem?
Exactly. And then they normalize that difference by the standard deviation of the rewards for that prompt.
So comparing apples to apples, kind of, and scaling by how much variation there was for that specific problem, the mean reward acts as a baseline, right, to reduce noise.
Precisely. Standard RL trick for variance reduction. But the authors were really digging into whether that normalization was the secret sauce or if something else was going on.
Which brings us to the whole negative samples thing. The assumption is usually RL methods using bad examples should beat methods using only good ones, like RAFT or even just supervised fine-tuning, SFT.
SFT just trains on correct input-output pairs. But these authors found, surprisingly, the gap between GRPO or Reinforce and RAFT wasn't that big.
Really?
Yeah, and even more, RAFT seemed to learn faster early on.
Huh. So that made them look closer at the negative signals, the wrong answers.
Exactly. And they hit on something crucial. It seems that prompts where the model got every single answer wrong were actually hurting performance.
Wait, training on batches of pure failure was bad?
Apparently so, a really significant finding. And they also found the reward normalization in GRPO, the mean and standard deviation part, seemed to have minimal impact on its own.
Wow. Okay, that's a real aha moment. So not all data is good data. Some negative data might be actively harmful. That's huge for practitioners.
Definitely makes you rethink how you use failures. They ran a bunch of ablation studies to nail this down, using Quen and Llama models.
Right, let's walk through those findings. First, RAFT's performance again.
They confirmed it. RAFT was competitive with GRPO, small gap, faster early convergence.
But there was a catch, right, about entropy.
Yes. Because RAFT only sees correct answers, the model quickly becomes very confident its policy entropy drops fast.
Entropy, like how diverse or random its outputs are. High entropy means it tries different things. Low entropy means it sticks to one path.
Exactly. Low entropy means less exploration. It finds a way that works and sticks to it. Great for speed initially, but it stops exploring potentially better reasoning paths later on.
So GRPO, by keeping some mix of good and bad examples, maintained more exploration and eventually overtook RAFT.
That's the hypothesis, and the results seem to support it. Early speed versus long-term exploration potential.
Okay, finding 2. Those harmful prompts where everything was wrong.
They confirmed it. For on-policy methods like Reinforce, feeding it batches where all samples were incorrect significantly hurt the final performance.
And GRPO avoids this.
Largely, yes. Its advantage calculation naturally downweights or ignores prompts where all responses have very low reward. So GRPO's edge over basic Reinforce seems to come mostly from this implicit filtering.
Not the explicit normalization math itself.
Much less so, according to their ablations. The normalization part had minimal independent effect.
Fascinating. Okay, finding 3. This led them to propose Reinforce-Rej.
Right. If prompts where all answers are wrong are bad, and maybe prompts where all answers are right aren't super useful for learning either.
Wait, why filter the all-correct ones too?
The idea might be that if the model finds a problem trivially easy, there's not much gradient signal, not much left to learn there. Focusing on the prompts where there's a mix of success and failure might be more efficient for pushing the boundary.
Okay.
Yeah.
So Reinforce-Rej filters prompts where either all responses are wrong or all are right.
Exactly, a minimal tweak to Reinforce. And they found it performed comparably to GRPO in the end, but was more KL efficient.
KL efficiency, meaning it improved without drastically changing the underlying model distribution as much. Smoother learning. KL is Kullback-Leibler divergence, measuring distribution difference.
Yeah, less disruptive changes to the policy for the same amount of reward gain, basically.
They did even more ablations, though, right? Like RAFT plus.
They did. They added important sampling and PPO-style clipping to RAFT, create an RAFT plus repair.
And that helped.
It improved final accuracy over plain RAFT. Yeah, faster convergence, too. Interestingly, RAFT++ without clipping did worse than vanilla RAFT.
So the clipping, even if not used often, is important for stability. Prevents huge updates when things diverge.
Seems so. But again, even RAFT++ showed faster early learning, but then plateaued and was eventually overtaken by GRPO.
The exploration issue again.
Likely. The lack of negative samples limits its ability to keep exploring and improving beyond a certain point.
Did they look at the entropy directly?
Yep. Compared RAFT++ and GRPO. RAFT++ policy entropy plummeted much faster. Once it got low, performance flattened out. Less exploration, fewer diverse reasoning paths tried.
While GRPO maintained higher entropy.
Correct. The negative samples, even if some are bad, seem to help maintain exploration, prevent the model from collapsing into just one way of thinking.
Makes sense. They tried tweaking RAFT++ with clip higher.
Yeah, a small modification to the clipping bounds on Llama. It helped stabilize the entropy a bit longer and improved RAFT++ performance in later training stages. Still, it highlights the challenge.
So finally, they really tore GRPO apart to see what made it tick.
Right. Compared standard reinforced to versions with different components added or removed.
Like Reinforced just removing the all wrong prompts.
Exactly. And that version, Reinforce plus remove all wrong, showed a big jump in performance over standard Reinforce. Clear evidence those prompts are harmful.
What about removing only the all correct ones?
Didn't help much on its own.
And removing both, which is Reinforce-Rej.
That led to better entropy, slightly better reward, suggests improved exploration balance maybe.
What about adding just the normalization, the mean centering?
That actually increased KL divergence and didn't help the reward. Maybe instability.
And adding the standard deviation normalization on top of removing both.
Very minimal extra gain.
So, boiling it all down, GRPO works well mainly because it effectively filters out those batches of purely wrong answers.
That seems to be the core conclusion from their analysis. The fancy normalization is less critical than the sample selection aspect.
And Reinforce-Rej, which does that filtering explicitly, both all wrong and all right, emerges as a simpler yet strong alternative.
Exactly. And their benchmark results across data sets like Math 500, Minerva Math, Olympiad Bench seem to back this up. RAFT and RFT++ held their own surprisingly well.
Okay, wow. So let's unpack the implications here. For folks training these models, what's the big message?
I think it's a call to maybe simplify, or at least to be very intentional about the data you use for RL fine-tuning. Maybe complex algorithms aren't always the answer.
The effectiveness of basic RAFT really drives that home.
It does. And the finding about harmful negative samples, specifically the all incorrect prompts, is super practical. Don't just throw all your failures into the RL training mix without thinking.
Right. Be smarter about sample selection. Reinforce-Rej seems like a good, simple starting point for that.
Yeah, the authors position RAFT and Reinforce-Rej as strong, interpretable baselines. They argue future work should focus on principled ways to use negative samples, not just assuming they're always helpful.
This definitely gives us a lot to chew on. How do we get better at spotting and filtering these bad negatives? What is the perfect exploration-exploitation balance for these LLMs? Could we simplify even further?
All great questions. And it's fantastic they released the code on GitHub so people can dig in themselves and build on this.
Absolutely. What's your final take on this paper?
I think it's incredibly valuable. It's a great example of how stepping back, questioning assumptions, and rigorously analyzing simpler methods can lead to really important insights. The idea that sample filtering might be more potent than algorithmic complexity here, that's a lesson that resonates. Think carefully about your data.
Couldn't agree more. A really insightful piece of work. Huge thanks for walking us through it.
My pleasure.
And for everyone listening, we hope this deep dive clarified the paper's findings and implications. Do check out the code if you want to explore further. Think about what this means for your own work or understanding. What experiments would you run next? Keep pondering those questions. Thanks for joining us.